Welcome to the module Robot Control. Now that you are already familiar with mechanical and electrical hardware of the robot, we have already learned kinematics, we have learned dynamics that are necessary prerequisite to make a robot capable to do some variable motion, to do any task. We now should be able to run this robot as desired by the robot input commands and not deviate too much from the desired commands. Got it? So that is the reason the control is there. A robot is to be controlled. So in this module, we'll do some preliminary learning in robot control, because robot control as such is a vast subject. So over here, as because we are targeting to handle industrial robot, we should be familiar with few terminologies mostly and with basics of robot control. So this module has objective to do that kind of learning over here. So in this module, we'll learn how a robot is controlled, and that will enable us to understand various concepts that goes in the background in a controller, which keeps the track of any error in the commanded and the actual positions or even in trajectory. So it keeps a track of the error and does necessary correction in real time while the robot is moving or when it is standing still in any pose. So okay, let us begin this module and understand what I am trying to say now. Okay, so let us begin. So yes, so in this module basically we'll be doing particularly in today's class, so I'll be introducing you to robot control, linear control system, spring mass damper model I'll discuss, and control and stability analysis we'll do later on in other lectures. Okay, so and transfer function, state space representation of a robotic joint. A robotic joint basically with a DC motor model will try to apply it to any standard robot. Even if it is a synchronous controlled robot, a DC motor model is very well applicable, as because you see even a synchronous motor works in a similar way. So there are few fundamental equation which doesn't change much even in case of those motors, particularly tau is equal to km into Ia. If you have seen it earlier in the actuator model, you must have noticed torque is proportional to current. Motor constant was given by some constant which is known as km. So you see that fundamental equation that remains the same, and that is the most specific one which actually works over here. So that is the reason the control we are handling in this class is applicable to most of different kinds of robots, which has various other kinds of actuators also. Feedback control system, we'll try to understand what it is, what does it mean, and how does it work, how they are implemented in robot. Okay, performance and stability thing we'll discuss. Proportional, integral, and derivative control, that is most commonly used kind of control in industrial robot. So we'll familiarize ourselves with this. Okay, and combination of PD control, that is proportional derivative control, proportional integral control, and combination of all these three, that is PID control, I'll discuss, and gain tuning in particular we'll discuss towards the end of this module. Okay, why we are doing control at all actually? So as because we know if it is an ideal robot, if we have designed something in CAD and the manufacturer is able to make it as it is, so that is a remote possibility, you see. Why? Because there are some manufacturing uncertainties also, and if we think robot, let us say I have given a dimension of 600 mm, so it may be possible that the distance between two joints is not 600 mm, it is 600.5 mm. Okay, and similar is the case if we see we have designed two axes to be 100% parallel. Okay, those are the two joints. So that also may not be possible. There exists a kind of twist between two particular joints next to next. So even if we have designed however accurately, manufacturing uncertainties are always there, and that is what is creating this error. Okay, so this link twist is there even if it is not there in DH parameter in ideal condition. So after manufacturing there might be some possibility that this is there. And even joint offset, same is true even for joint offset. There do exist joint offset even if there is no joint offset in the design itself. So you got it. So manufacturing error is always there, and sometimes they are not even measurable once it is assembled. So in that case we have to take all those in control. All those uncertainties is to be dealt by the controller itself. Okay, it cannot be calibrated also. Okay, so by some sort of calibration we can go again very near to the model or very near to the actual assembly of the robot. But yes, you cannot go accurately. In that case, controller takes care of rest of the uncertainties in the manufacturing of the robot which has happened. Okay, so that is there. And mass moment inertia, you see, mass and moment of inertia, those are again some parameters which are again not known to very close extent to the design thing, or very accurate mass values we don't know for a link also. Same is for moment of inertia, because there are a few components that goes into the robot assembly which were not planned. Quite a lot of time they are not very accurate also, like cables. Cables, however accurate you are, when it is manufactured, when it is assembled, when it is moving, so it can be a little saggy, it can be routed somewhere else. Okay, so accurate design, taking care of that and getting perfect knowledge of cables is very very difficult. Okay, so that makes again it is incorrect model. Okay, so and that cannot be taken care of by the dynamic equation of motion which is given here. So it should have moment of inertia accurately, right? It should have h and c values which are calculated based on that. So they all contain the masses over here, and these components of the torque equation. Okay, over here it is also there. So you see, moment of inertia and masses should be known very accurately. That again, because it is not possible, so it cannot be taken care alone by this equation. So this equation can no more run the robot accurately. So you need to have some sort of controller that takes care of any error which happens due to unmodeled parameters which are not taken care of over here. Okay, so yes, and then there are changes in payload. Yes, today this robot is handling, a robot is sold and used by the payload capacity that it can handle. Let us say if it is a 5 or 20 kg payload capacity robot, it is not always true that it carries 20 kg. Sometimes it is carrying, let's say, an empty carton which is not 20 kg and it is just 5 kg. So that gives you the complete range of the weight that it can handle. Okay, and even while picking and placing, sometimes it is picking just 5 kg, sometimes it is taking 20 kgs, and you are not adjusting the controller gains, you are not adjusting anything while the robot is running. Okay, so during runtime only controller has to take care of all these variations that can happen to the payload also. That causes, you very well know that these causes the mass properties, inertia property of the robot dynamic model. Okay, so whatever goes into this dynamic model, these masses do affect all the parameters which are here in this equation. Okay, and again this equation never took care of any friction if it is there in the joint, any backlash if it is there in the gears, transmission gears, and any other non-linearities in the mathematical model which is given by this equation. Got it? So using this is not sufficient. You have to either identify those non-linearities if it is there, or you have to take care by the controller itself. How does the controller take care of all those uncertainties? So we'll discuss in this today's class a bit, and then in this module later on also. Okay, so these are some of the requirement why a robot controller is required. Okay, so now in this uh, module basically we'll be doing mostly linear control here, and systems are represented mostly by linear differential equation. To be more specific, we'll handle mostly second order linear differential equations. So as because most of the systems what we are handling now can be taken care of well by second order differential equations, and we should be happy with that. So I'll show you how to use just this, work with this limitation, and still you can do quite good amount of control of your industrial robot. Yes, so what is linear control? So what do you mean by a linear differential equation first of all? So a linear differential equation may be given as, let's say if it is a0x y plus a1x y dash a2x y double dash and so on so forth till anx y n equal to bx. Okay, so let us say this is the equation where you have y dash, y double dash, y triple dash and so on so forth till yn dash. They are all derivatives of unknown function y, which is a function of x. Y is a function of x. These are all their derivatives. Okay, and what are a0, a1, a2, an? They are arbitrary differential function. And they need not to be linear. They can be, let's say, sin x, they can be log x, right? So anything can be here. So all these this basically defines your linear differential equation. So our system, what we are going to handle with this kind of controller, which we are going to discuss in this module, system should be capable of represented in this kind of linear differential equation. We will also be doing feedback or a closed loop control system. So how does it look like again? So let us say you have a robot, okay, and that is commanded by some kind of torque over here. Torque, basically we don't command directly by torque, we command by current, let us say, that goes to the motors of the robot. Okay, so it gives you some kind of output, and this current is fed by a type of power amplifier. Let us say here you have power amplifier, okay, that actually converts the small input signal that are the output of a type system which is known as a controller. Controller is here, that gives you a small signal which will tell this power amplifier, now you feed this current. Okay, so this current is basically decided by the controller output, and this is nothing but a power amplifier, because you know this signal is not good enough to directly drive the motors which are there in your robot, which is here. Okay, so you have your robot which goes here. Okay, this is driven by the huge amount of current which is here, but this is nothing but the signal that comes out of the controller. Okay, so now what goes to the controller? So basically you have a feedback line that actually is fed back like this through some kind of transducer or some transfer conditioning system, signal conditioning system. So finally it comes to a comparator. Okay, and this is nothing but the error. Okay, and this is the signal, that is the desired signal. Okay, the desired signal, whatever position you want to go, whatever set of points you want to traverse, so all the sets are given over here, actual values are fed back from here. So this line is known as feedback line. Okay, this is your transducer. Finally it goes here. So both the signals are of same kind now, and this comparator basically compares and finds the error goes to the controller can be a PID controller, it can be of various type, we will discuss later. So this controller gives you a signal. So this whole of this system which is here is known as a controller, and this is a closed loop control. So we'll be dealing with this in this module also. Okay, so how a typical industrial robots are linear, why we can be assured that our robot can be controlled by simplifying our system to a linear system. Okay, it can be handled by a controller which is a linear controller. Okay, so that is assured by few things which are noted here one by one. So driving system of these joints, they have huge amount of gears. Okay, so first link, let's say you have, and then you have a gearbox, then comes your second link. Okay, so this is a gearbox which is here, and it can be 300 times gear reduction over here. So in order to multiply the torque, so torque at the input is very less as compared to torque at the output. Okay, so what happens, it is basically a reducer. Okay, it reduces the speed and enhances the torque. Okay, basically the fundamental equation for this is tau 1 omega 1 is equal to tau 2 omega 2. So if you reduce the speed, you get the higher torque. So that is what is the reason why it should be here. So you have a gear reduction which is here. So this, doing it like this, linearizes your system dynamics. So we'll again see when we'll do a DC motor modeling for our joint. So we'll see there are electromechanical features which goes into that model. So electrical and mechanical thing, finally your system gets very much like a linear system if you have a huge gear reduction. Okay, so this basically isolates this link from this link. So handling this link, second link which comes next to the first link, so this can be handled without worrying what is going to come over here. And even the joint which is over here which is driving this link, so this joint also can be handled independently. So you need not to worry what torque this link is going to transfer. So basically both are isolated. They can be treated like a isolated link. You need not to worry what kind of effect does this link is going to do on this link. So they are decoupled that way. So presence of gear makes things very simpler. They not just, it helps us to enhance the torque and reduce the speed so as to make it more controllable. It also isolates the joints from one joint to the other, from one link to other. So you need not to worry about all that. So mass and inertia terms are reduced by the square of gear ratio. This is what is proven later in one of the lecture in this module only. Okay, so you see the effect of mass, the effect of inertia that basically the next link is going to put on the previous one is very less. It is reduced by square of the gear ratio. Okay, so you can imagine if it is 100 times you are squaring, so effective mass that the previous link sees, okay, the effect of mass that comes here, m2 comes to here, is reduced by 100 square if the gear ratio is 100, you see. So that is what we are going to prove later on also. Okay, so doing so, joint dynamics is decoupled. Okay, you can treat them independently and each joint can be controlled independently. Okay, so one of the link is not going to have effect of its motion onto the other. Okay, so that is what is isolation here, I mean. So single input, single output control is easily possible rather than multiple input, multiple output. Okay, so this is what is industrial robot is. Okay, so that is what is simplifying your system to a greater extent. Okay, and majority of industrial robots, they work like this. And um, again, we'll be using DC motor model to make you understand all these theories, but yes, they are quite nearly applicable even with any other kind of robot motors that you see, even for AC synchronous motor, which are mostly present in industrial robot. So that this theory is also applicable for that. Okay, so yes, so what are the control techniques that are there? So just now you saw how does a closed loop system look like. So yes, it can be controlled by simply switching on and off. Let us say you have a ceiling fan in your home. Okay, so yes, there are multiple ways to make it go at a particular speed. So one way of doing so, you just switch it on, keep it on for a moment. By the time it reaches some speed, you switch it off. Okay, it reaches to a value, switch it off. It gradually will start reducing its speed due to friction, air drag and all. Finally it will reduce. So if it comes down significantly to some value below certain value, again switch it on. Okay, so you can keep switching on and off, and you can make that fan rotate within certain range. Okay, so that is one way of controlling it. That is known as a two-step control, and your system behaves like this. It picks up speed, reduces, again picks up, reduces. So every time you switch on, you go like this, switch off, you come down, switch on. So that way you can definitely control speed. In a similar manner, you can even control the position, and you can handle different other parameters also. Okay, so that is one controller. Others could be proportional, integral and derivative control. This is quite frequently used in industry for various, not just robots, for many other equipments also which are there in the industry. Okay, so we'll go very much in detail in this type of controller. Okay, and non-conventional controllers are also there. Some intelligent controllers are there, AI based control systems are there, adaptive controllers are there. Okay, so the different other types of controllers are also there, which are normally not there in the industry nowadays. With cobots, yes, you do see even those kind of controllers. Okay, so but we'll focus ourselves mostly to this one in this module. Okay, so yes, even with the control system over here, okay, even placing all the controls in place, you still have possibility that your robot can go unstable. What is stable, what is unstable? If you remember a ball problem in which you have a ball placed in a ball, so this is a ball, this is ball. Okay, so if you leave this ball anywhere on this ball, so it will automatically come to the lowermost position. Got it? So but if you have a situation which is something like this, so in this, if you move this ball even by small displacement, it will quickly go unstable and it will fall down. Got it? So this is unstable, this is stable. Got it? So two different kind of equilibrium, you must be knowing this. And there is one more kind which is known as a neutral one. So this is stable anywhere on this plane. If it is a plane, flat plane, you can leave this ball anywhere on this plane and it is okay. Okay, it is neither unstable nor stable. It is known as a neutral equilibrium. So this kind of situations do exist. So we'll try to work around so that we be in this. So that is what some issues are there with that. The reason why we are using controller is very much due to this also. Okay, so this is all about linear control and the kind of controllers we are going to do. Okay, so how does a typical industrial robot controller is? So just now I have drawn a detailed layout of one of the joint. So this is a set of joints. How does it work in a robot? So this is your robot manipulator. Okay, you have a robot manipulator that basically is driven by the torque. As I have told just now, you cannot command directly by the torque. So you do command by the current that goes into the actuator. I am talking about electrical actuators over here. So torque is not directly fed. So if I tell torque, that means it is current that goes to the actuator. So torque, yes, it is Km into I. So if it is a current, so current is proportional to the torque that is desired. So there is something which is known as a power amplifier that is there in between. So that is implicit everywhere if I say that. So output of the robot is velocity of the joint, position of the joint. So two sensors are there. These are feedback lines, feedbacks that goes to the control system which is here. So this basically is the brain of whole of your robot. So this takes input from the trajectory planner. If I want to do a welding, I want to move in air and do some painting operation, so those trajectories are fed from here. What is this? This is a set of position that is fed, velocity that is required at each moment when you go along, and this is the acceleration that you want at every instant of time. Okay, so all these three are fed to the control system, and controller basically tries to maintain to this desired trajectory. That is the input, that is the commanded input. Okay, so it compares with the actual one to the desired one, and it has its own brain. Based on that, it does everything. So you see, this is a typical robot control system. We'll talk about what actually goes here, how it is possible to basically do this. Okay, so a typical structure of industrial robot transmission system with its links, it looks like this. Okay, so you have a motor, you have gearbox, sometimes they are belts, and then you have another link, you have another motor that goes on top of this. Okay, this motor again has got a gear reduction here. This was gear reduction 1, and then again you have a link which comes here. So this is how it is made. Okay, so you have current and voltage that comes here to the motor. Okay, and this is the output joint variable. Okay, so this is how I assume all the robots are made. Yes, there are few differences at times. You may see belts over here. You can have direct transmission also. So there are possibility with some variations, but effectively, if I say it is gear, basically it is some reduction which is happening. It may be due to the size of two driving and driven pulley, and you have a belt that goes here. So even this is a reduction. This is a reduction. This is the driving pulley, this is the driven one. So if this rotates by 2 revolution, this will rotate, let us say, just by 1 revolution. Got it? So this is also a reduction. So if I say it is a gearbox, it can be due to various reasons. It can be combination of belt and gears also. Okay, so that is what is here. So now let us try to understand what a second order linear system look like. We are familiar with spring, mass, and a damper system. A typical mechanical system can be represented, simplified model can be this one. We'll see how a robot equation can also be represented like this later in this module. Okay, so for now, let us say you have a mass which is connected with a spring. Spring is attached to the wall which is here. This is nothing but a damper with damping constant which is given by B over here. Okay, so you know this equation very well. So if you draw a free body diagram of this, so you have, if you displace this by a small displacement delta x, so spring generates a force called K delta x, is it not? So if you move this way, so a spring is going to pull it this way, is it not? And again, if you are moving with certain velocity x dot, so again your damper will pull it this way, that is given by B x dot. So overall the system is in equilibrium. If you are moving with some acceleration. So you have a pseudo force that tries to act like this, and that is given by mx double dot. Is it not? So if you move like this, you see inertial force that comes like this. Okay, you have damping force, you have stiffness force. So combined all together, you can write your equation like this. So this is the cause which is actually creating this motion. So if you are pulling it by force F, so these are the components that are going to come. So this is the equation that you are going to see. So what is this equation? How does this system behave? Okay, so this can be represented, you know already, using this. What is this? If you remember, this is nothing but a spring mass damper system, right? So you have a damping constant which is given by this. This is known as a damping ratio. If you are familiar with simple harmonic motion in your high school physics, so you must have seen this probably. Even if you are not, we'll come back to this and we'll do it once again. Okay, and again, this your omega n, that is your natural frequency, that is given by square root of k by m. So if you leave this system to oscillate of its own without a damper, so it will oscillate with this frequency k by m root over. So that is the natural frequency. Okay, so as a function of time xt is the displacement, which is as a function of time, it specifies the displacement of the block. So this depends on the block's initial condition of the displacement and the velocity as well. You may start from the mean position, or your system is already in a location and you have given it a velocity. So the boundary condition may change. Okay, but I assume if it has started from rest. So to solve this differential equation, I have assumed something like this. You have to substitute x is equal to e to the power st, s is a constant. The solution would depend on the characteristics equation which is given by this. Try substituting this. What you do get is, if x is e to the power st, so what you get, x dot is s e to the power st. Similarly, x double dot will give you s square e to the power st. Is it not? So if you substitute all these to this, x double dot, x dot and x directly, you can take e to the power st common out here and you are remaining with ms square bs plus k. What is this? This is basically known as the characteristics equation of this. Okay, characteristics equation of this. Okay, which has roots given by S1, 2. There are two roots because this is a quadratic equation. So S1 is positive of this, S2 is given by negative of this. Okay, so there are two roots which are there. Based on the characteristics of these roots, your system has some behavior. That is what we will discuss now. So this system can also be treated like this. What makes this system to be treated like this? Basically, this was your fundamental equation. M force is equal to mx double dot plus bx dot plus kx. So if you take Laplace on both the sides, what do you get? So it is fs equal to ms square xs plus bs xs plus k xs. So if you take all these common, so what do you get? xs into ms square plus bs plus k is equal to fs. Okay, so you got it. So now this is your output and this is your cause, that is the input. So output by input is also known as open loop transfer function. So it is given by GS. So what do you see here? Output by input can be written as 1 by ms square bs plus k. What is it? This is nothing but the transfer function. So the part which is here can have multiple roots, and this is the reason why this is known as characteristics equation. If the denominator goes 0, so it will have certain value. So if the denominator that is given by the characteristics equation, so that governs the type of gain that you are going to get. Okay, so that is actually governing the system output and input relationship. Okay, so yes, so now I am again expressing it in the way omega n, that was natural frequency of the system, you know that. So omega n, this is the damping ratio of the moving block. So if I use these two substitution to this, I can write the same equation like this. Okay, and again the two poles which are there are this is nothing but roots of the equation this. So this is given by the discriminant, which is here, b square minus 4mk. So this equation can now be written like this. Okay, so it is damping is ratio square minus 1, that is within the square root. This can be less than 1, greater than 1. So whole of the behavior of the system will be governed by this. Okay, we'll discuss very much in detail this, so don't worry, we'll come back to this once again. So the characteristics equation is formed by the equating the denominator to 0. Okay, so if we equate it to 0, basically we want to find out the roots of this equation. Okay, so these roots are also known as the poles of this equation, and that is going to control whole of the system type, the behavior of the system. So what could be the behavior of the system? Roots are real and unequal. That is the case when b square minus 4km is greater than 0. In this case, the system is overdamped, sluggish and non-oscillatory in nature. Okay, that means if you pull it, leave it, it gradually goes to the original position. Okay, it won't oscillate. Okay, so that is one behavior that you can see. Next one is roots are complex conjugates. That can happen only when b square minus 4km is less than 0. Okay, in this case the system is underdamped and oscillatory in nature. Oscillatory, the system will oscillate, but because it has some damping, so that oscillation will die off little bit in every next oscillation that it makes, and finally you see you can have a behavior which is something like this. Okay, so it will oscillate something like this. So this becomes your displacement and this is your time. So over the period of time it will oscillate about the mean position, and this will gradually decrease. So we'll discuss very much in detail this one. So this is an underdamped, okay, and oscillatory in nature. Okay, the third one is critically damped. This is a condition when b square minus 4km is exactly equal to 0. Okay, so this is the fastest non-oscillatory response. Your system is not going to oscillate. It will gradually go to the mean position, but this is the fastest way it can go to the mean position, faster than this also. Okay, so these are the three behavior that you can see. Okay, so that's all for today, and in the next class we'll deal this problem further very much in detail. That will discuss response of the second order linear system in the next lecture. So that's all for today. Thanks a lot.